Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. We are still continuing in the radical chemistry. If you remember, in the last class I talked about the photochemistry of carbonyl compound and I talked about the Norris type 1 and type 2 reactions. And if you remember, at the beginning you have a carbonyl compound, and once the UV ray fall on the carbonyl compound, there is N to pi star transition happen. Okay, so now we are going to talk about another reaction which I already mentioned in the last class, is the Petrano-Bucci reaction. So I am going to start with the Petrano-Bucci reaction, and then I am going to go to the enone alkene cycloaddition, some of the 2+2 cycloaddition reaction using enone. Then also I am going to talk about some of the aza Petrano-Bucci reactions and the dipymethane rearrangement. So let us start with the Petrano-Bucci reaction. So it is actually a very important cycloaddition in reaction between aldehyde or carbonyl or ketone with a alkene. So if you remember in the last class when I was talking about this, if you have a carbonyl compound, you remember there was a N to pi star transition. We talk about the different type of fate about it. So in one case I talk about the Norris type 1 reaction. If you remember, there is a generation of acyl in radical. Then there is a the type 2 reaction where there is a hydrogen abstraction happening, and the formation of the 1,4 diradical. So here I am going to talk about another important chemistry where you can do cycloaddition with a olefin. Okay, so that can able to form a important 4-member ring called oxetine. So why we are interested about this chemistry? Because this oxetine is present in several type of natural products. So you can see this 4-member oxygen ring here in this type of natural products. So now we are going to learn about the reaction mechanism. What is the mechanism of this Petrano-Bucci reaction? So there what is happening, first thing, as you know, once the N to pi star transition happen from the carbonyl compound, so it is going to the excited singlet state. Given here from the excited singlet state, it can directly go for a stereoselective reaction with the olefin to forming the product with high selectivity, or it can go for a singlet to triplet through intersystem crossing, and then it can, so this radical can now add to the corresponding olefin. Now it can form this 1,4 biradical going to form. Now here there is two things is happening. So first thing is, once this biradical is formation happening in the triplet state, there is a, at the same time there is a spin flip, at the same time there is a bond rotation happening. So once that is happening, this reaction become non-stereoselective. So you end up becoming a mixture. So now the question comes in this reaction, as I mentioned, so what type of compounds? So generally the aliphatic aldehydes and the others, I think aliphatic aldehydes you will see majorly formation of this from the singlet state, it is going for the Petrano-Bucci reactions. In case of aromatic ketones, you observe it is going through this type of formation of this the biradical species, and then there is a non-stereoselective reaction. So it's not only that is the not only the one important factor. It's not that if you are going through triplet only you will always get a get a mixture. There are some other important fact also I am going to discuss. So first important thing is this is happening, this chemistry happening due to the N pi star excitation of the carbonyl compound. And second thing is the excited singlet state, it can happen from the excited singlet state as I mentioned, or from the triplet state in case of aromatic carbonyl compound. So first thing is there is a formation of this type of biradical as I mentioned. So now the question comes, is there any evidence for that there is a biradical formation happening? So now if the Petrano-Bucci reaction happens between the benzophenone and this vinyl cyclopropane, then what is happening here, you can after formation of biradical, it can go to the corresponding product oxetine formation, or it can happen that from there is a cyclopropane ring opening happening, because cyclopropane is a strained ring. So if you have a radical here, it will allow the ring opening formation of this radical. Now there is a radical recombination between these two radicals, which can form this tetrahydroxypene. So once the tetrahydroxypene is going to form here, that kind of confirm that yes, it is gone through some sort of a biradical formation. There are other evidence here in this particular reaction. So so there is a alene here and there is a carbonyl compound. So they have isolated this this product. So this is also kind of giving explanation the formation of this type of biradical. So first thing, there is a N to pi star transition happening from singlet to triplet through the intersystem crossing. Okay, and then what is going to happen, you can see first thing is going to happen, this oxygen radical, and then it is going to react with this double bond here, formation of this radical species. Again this 1,4 radical species which go 1,4 biradical species which can form a bond here. And now what is going to happen, you can see there is a double bond here, and you have a acetone in the reaction. That is important fact, because once you have acetone in the reaction, it can also able to form that oxygen radical and the carbon radical, which can able to do a recombination again here. So there will be another Peyton-Ubuchi reactions with this olefin and the carbonyl group here to get to this product. So as this product formation is happening, this is kind of indicating that okay, if these radical are not forming, then how come this bond is forming here in between this carbon. Okay, so that is kind of a evidence for this biradical formation. So now we are going to learn about the important fact here, that if you have in this reaction, as I mentioned, that you have a carbonyl compound here. As I mentioned, it could be aliphatic or aromatic. So let me write R dash, and at the same time you have a olefin here. So the question comes, what type of group that olefin has? If the olefin with a electron donating group or a electron withdrawing group. So now the things come, depending on these, we are going to learn about that if you have chemistry with electron donating group versus electron withdrawing group, then there are two different scenarios going to happen. So before going that, we are going to learn that once the n pi star transition happen. So what is happening once the n pi star transition happening? Now if you try to look into your np orbital which have a single electron. So if you have and that is on the oxygen. So now what is going to happen? That is actually electrophilic in nature. That means it can only able to interact with a nucleophile or with a electron pair or with a pi electron cloud. Then now in the pi star case, what is happening? Pi star is actually nucleophilic, so now it can able to interact with a electrophilic. So that is a very important fact, because based on that you are going to see here that now if you try to think about the reaction with a olefin which is having a electron donating group. Now if you try to think about your carbonyl compound, n pi star orbital, n is your HOMO having these 2 electron here, and if you have electron donating group, then your the pi bond will be a little bit higher in energy, so that will be the HOMO, and that is the pi star orbital. Once you put H nu, what is going to happen? It will from the n it will go to the excited state, correct? So that is happening from n, it is going to the excited state, so it is going to n to pi star transition is happening. Then what is going to happen? Now if you look into it, you have a pi electron here in the olefin, and you have this n, so now what is going to happen? Now this n and pi going to interact with each other. So there will be a photo-induced electron transfer going to happen from here to here. Okay. So that can able to form this radical ion pair, and at the end it is going to form this type of biradical species, and then it is going to form to the corresponding product. So now the question is that if you have this type of electron donating group, they are going to actually interact. So the way we are trying to draw here, so we can this is your np orbital and that is the pi, and I think we can draw here which I think this could be a 1 electron here. So now what is going to happen? They are actually interacting in a perpendicular approach. So that means kind of a 90-degree approach. So you are seeing here, this is your n and that is your pi. So that's how they are actually forming this then after the intersystem crossing, they are forming this biradical, and then from there it is going to form to the corresponding product. So the thing is, as it is forming a biradical, that this reaction is non-stereospecific, as I mentioned at the beginning. Now the question comes, if you have electron deficient or electron poor or alkene. So now if you try to look into this molecular orbital picture here, you have this n pi star here. But now if you have electron deficient one, you can think about now what is going to happen, it will decrease the pi density. So the pi will be more stabilized for that particular double bond, and then there will be a pi star. So what is going to happen, as after if once you find the UV light, it is going to go for you can see it is going to, I think it is going to go for this is there is an error here, it is going to go for this n2 pi star here, and this will kind of remain sorry for that. Okay, so it will remain here, so it will go for the n2 pi star, and then now what is going to happen, you can see here, this is the pi star, going to interact the another pi star here, because if you remember I was talking about at the beginning that the pi star going to like to interact with the electrophile. Okay. So, these two pi star now going to interact, and now once these two pi star going to approach to each other, they are going to approach in a parallel approach. Okay. And what is going to happen? They are going to form some sort of a exciplex. Okay. So, in exciplex actually there are two conjugate molecule in the excited states. Once they are forming this exciplex, that means, and then one of them will be in the excited states, and one of them, so they in the excited states of this ketone is forming exciplex with this double bond compound, and then through a concerted reaction they are forming the product. So, that is why the reaction is stereospecific in case of the electron. So, if you have electron withdrawing in olefin, then the reactions are mostly stereospecific. So, now the important fact here that you can see here in the carbonyl case you have an oxygen and a carbon, and so now the question comes, and in case of electron donating group, so there are two different sides. It could be head. So, it could be so is it going to happen from the both in the head or from the head and tail? What is going to happen here? So, because you can see there are two different possibilities. Let us try to write it down for a simplified things, that if you have a carbonyl group here, and if you have a, suppose you have an electron donating group, then what are the possibility? What are the two different oxygen going to form? It can form this one, with electron donating group, or it can form the other one, correct. Now, the question comes which one will be major and which one will be minor, and the same thing if you have an electron withdrawing group, then what will be the scenario. So, now if you try to understand that once you have this species, once you have this oxo radical species, this can add here, and now the question comes, what are the different possibilities? It can add here or it can add here. So, that way you will be ending up two different scenario here. So, there will be two different type of biradical we are talking about. In one cases you have this radical next to electron donating group here, versus you have this a primary radical. So, now if you look into it, this will be a more stable radical. So, this will end up giving this as a major, maybe around 60 to 70% this will be the product, and the rest will be the this product in case of electron donating group. Now, if you come for electron withdrawing group, as we mentioned, it is going to form some sort of exciplex. So, it is a complex form between two different conjugated molecule, and one of which are in the excited state, as I mentioned. So, now the thing is, as the reaction is going through a concerted things, we can think about some sort of deuterionic species where there is a delta plus delta minus. So, now we are trying to explain from here. So, now the question comes, if you think about this carbonyl group, correct, we always know that if I have a carbonyl group, okay, what we are very familiar with, that there will be delta minus here, delta plus here, we all know about this, correct. So, but you have to important thing you have to understand. So, this is all about in the ground state. What is happening once you are going to the excited state? You have seen in the excited state what you are happening, we are making this O dot and then C dot, correct. So, now the scenario is getting changed. Once you are making this, now this oxygen dot species, so now the oxygen center actually becoming a electrophile, let's say electrophilic, because it is a oxygen with a radical species. I have already mentioned that in the radical chemistry also. So, now you have a scenario that this will be a delta plus and this will be a delta minus, correct. So, now if you think about this, that you have a delta plus here and delta minus here, now it can if you have electron withdrawing group, if for electron withdrawing group pull the electron density from this carbon more, because it is going to take the electron density. So, that is how if you try to draw the resonance structure, you can clearly see that. So, if you have suppose you have some sort of a carbonyl group or something like that, then you will see that there will be a plus and there will be a minus here. If you try to draw like a resonance structure, that means you will see there is a delta plus here in this carbon and there will be minus in this carbon. So, now what is going to happen? This is the way they can form bonds. So, that means the oxygen will be with this carbon where you have electron withdrawing group, and the next carbon will be with the other side. So that can give this product as a major product. So now there is an important concept we just now learn about this perpendicular and the parallel approach, and the important difference, as you have seen, that in case of the parallel approach you have seen that they have to kind of approach through the from the top or the bottom faces, correct, and the perpendicular approach you have seen in case of the np orbital and the pi interaction. So now if you have a one double bond which is electron withdrawing group, two cyano group versus two OET group, that means they are electron donating versus electron withdrawing, and we are talking about the fluorescence quenching of these starting materials. So what is happening here, once you see that in this particular compound we are seeing the quenching is higher in case of the dicyano compound compared to the here once you have a two OET group here. So because what is going to happen that once you have this carbonyl here, now this can coming from the up or down, which is happening very very comfortably compared to the facial approach. Okay, but now what is going to happen, and if you have a scenario here, once you try to bring some sort of a steric, that means once you are try to bring a dimethyl group here, now you see the ratio is not not great. So there is not much selectivity between a perpendicular approach versus a parallel approach. But as soon as you bring this dimethyl here, then dimethyl in this carbon, now what is going to happen? Now this approach becoming slow. What is going to happen? Now this approach where it is going to come from the like in a perpendicular approach. So the perpendicular approach between this group becoming now slow here. Okay, once you are having this bulky group here, the perpendicular approach becoming slower. So now what is going to happen? Now this approach from the up and down has not get much effect here. So you will see this one still getting major, and this is really minor here. So you are seeing that once you are bringing the steric factor, what is happening? The perpendicular approach getting actually affected much compared to the parallel approach using the electron deficient olefin. So there is another important fact about the Peter-Novici reactions, that if you have a olefin here, in this case you have olefin and your carbonyl group, once you put a H nu, what is going to happen? You see formation of this O dot and the C dot. Now you have to understand there is two different possibility. If you have a carbon here, which two carbon, so what will be the the regioselectivity? So that is the important fact here. We are trying to show you that there is a possibility that the oxygen forms bond here, forms a radical here, and these two radical combined, or it can form the oxygen form a bond with this methyl radical here and then form this radical and they can combine. So which will be the ideal scenario? Again that actually depending on the which radical will be more stable here. So after you can see here this radical will be a tertiary and this will be a secondary. So here so this will be the winner, that's how you end up getting to the this product as a major product, which will be converted to a natural product after few steps. Then the enantiomer control and the diastereomers control. So we now go to talk about that. Suppose if you want to make a diastereomers control here with the ester group, if you try to bring the 8-phenyl methyl group here. Once you bring the methyl group, what is going to happen? This win planes of this 8-phenyl methyl, you can clearly see that if this if you have a carbonyl group, then the carbonyl have a two different phase, correct? So that you have to control, and that can be controlled when you have this bulky group, then this facial approach or formation of the bond through that side is getting blocked. So now only approach is remaining through this side. So that's how you can able to control so you can improve the diastereoselectivity up to 96% using that. So there are some more example to the synthesis of important compound. Again you can see the pattern which reaction with the benzaldehyde and with this compound you can get to the very high high stereoselective product. There is another example here with furan. This can also participate with the Peter-Novici reactions, and you can see it can form the product with high stereoselectivity, which can able to convert to the natural product. Again, I think there are more example, and there are also different aspects about the Peter-Novici reaction. So there are another important fact that once this diradical formation happening and finally that two bonds are formation happening, the steric also play an important role. Okay, so I think I already give the reference of the Nicholas Turo book. I think it's a very good book for the photochemistry. So you can also go through that book. There are more example. Also there is a very good NPTEL lecture by Professor N.D. Pradeep Singh of our department. You can also definitely go through his lecture as well. So now I am going to show you another important example for the intramolecular version. You can see here again there is a formation of this O dot and the C dot, which can able to form this bond to here to form the finally to the oxytocin. So now it is not always with the carbonyl, it can also happen with the imine, and once it is happen with the imine, we call it as a Petano-Bucci reaction. Again, instead of what is going to happen, now you have a 4 member doing with nitrogen, so it can form a azitine. Okay. So there are more example here. You can see here you have a imine here, and now you have a double bond with the electron donating group. You have end up making this product here. Okay. I think you can also try to follow the concept which I have teach you for the formation of the why it is forming this, not the other one, correct. And now you can see another example here, very similar substrates, and we also end up getting to the this sort of product here. So now I am going to move to the Petano-Bucci reaction, and I think I will give you more problem to solve during the homework. So every week there is assignment, you guys know already, so I am going to give you some more problems there. So now I am going to move to the Petano-Bucci and talk about another important photochemical reaction about the carbonyl groups. This is the enone 2+2 cycloaddition. So I think we have already seen that if you have a carbonyl group and if you have a olefin, then you end up getting to the Petano-Bucci product, and that is majorly happening from the N pi star, correct. So I think it is happening from the N pi star, that is the first step. So it could be a singlet or triplet depending on the substrate, but the N pi star transition is the important transition there. But now we are going to learn that there is a double bond here. In case of enone, you can see there is a olefin also here. So that olefin can also take part in a 2+2 cycloaddition here to form this product. So that is now we are going to discuss. You are going to see here the major chemistry here with the enone 2+ cycloaddition actually happening from the pi star. Okay. So let's I think try to understand that. We have already know that if you have a olefin here, there is a pi and pi star, correct. We already know that. And if you have a carbonyl group, we have seen that in case of carbonyl group there is a N to pi star transition can happen, or there is a pi to pi star transition can happen. But now we comes to enone. So enone is a mixture of the double bond and the carbonyl compound. So what you are going to see here, now you are going to see not only one pi bond, you are going to see there are two pi bond. One is from the double bond here with the, and then one is with the carbonyl. So there will be a pi 1, pi 2, and then there is a non-bonding electron. At the same time there will be this pi star orbital as well. So these will be the anti-bonding orbitals, and these are going to be the bonding orbital. And the important fact you are going to see in case of enone, that once it will go for the intersystem crossing, so once it will come to the S2 to S1, so once it will go to the S2 come to the S1, and then it can go for a intersystem crossing. And now it can have that it can again you will see there will be N pi star and the pi star, but in case of enone the N pi star and pi star gap is really small. So a lot of times you will see the pi star will be the triplet will be the lowest energy compared to the N pi star, and some cases depending on the structure of the enone, you will see some cases also the N pi star going to the lowest energy triplet state. So now what is happening here, what is the mechanism of this type of enone 2+2 reaction? First it is going to excite to the singlet, then it will be going to the triplet through the intersystem crossing, and then it is going to form a exciplex with the olefin, okay, and from there it is going to form this triplet diradical, and then it is going to finally form this form the product. So again the low energy pi star state is responsible for this enone undergo cycloaddition. As I mentioned here, the pi star energy is major cases you will see the lowest triplet state. So we already know why the 2+2 does not happen thermally. You must have already read in the photochemistry that if you try to draw the HOMO and LUMO and try to so you have seen that already. I think that if you think about the LUMO and HOMO in case of just 2+2 cycloaddition, if this is your LUMO and this is my HOMO. So what is going to happen here? You can see in one case you will see a bonding, and the other case you will see anti-bonding. Okay. So that's how we see that 2+2 cycloaddition in case of enone, it is happening the photochemically, correct. So now the the involvement of the biradical. So suppose if you do the reaction with this enone and this double bond here, what is happening? it is going to actually, you are going to see that it is not only giving you the product with the cyclobutane, but at the same time we are also isolating other products. We are isolating this product as 2.9%, then this is the other the regioisomer around 19%, and we are also getting to this product. So, and also now if you use a vinyl cyclopropane, the similar thing is happening. Not only we are getting this the product, we are majorly getting to the ring opening of the cyclopropane. So, this kind of indicate that why this is happening, because if you try to think about how this product is forming, then you have to think about what is happened, that once you, so this is definitely happening because you have a radical species here, you have a radical species here, and you have a cyclopropane here, correct. So, now that is the scenario as I mentioned, cyclopropane, the strain ring that is going to open up, and once that is going to open up, it is going to form this species here, and at the same time it is going to form a double bond, and then you will end up seeing that happening, because if you have a double bond here, as you can see, that can end up making two one carbon here, you will see a radical species here, okay. So, now what is going to happen, of course these radical species can once you are forming this radical species, they can go for the hydrogen atom abstraction, and you can end up seeing this type of products here. So, that kind of indicate that there must be some sort of the biradical formation happen, that is how these type of products are isolated. And then you can see here the question comes also that why this product is formation happening, the 2.9% or this 9.1%, what is this product is coming from. Now, if you try to think about how these products are generating, then you have to try to think about this type of. So, now you can think about here that once you are forming this product, let us think about here. So, once you have a radical species like this, instead of the radical recombination, what is happening, it can also go for hydrogen atom abstraction. So, this can go for hydrogen atom abstraction from the CH3, and once that is happening, you can, and then this is also going for hydrogen atom abstraction to end up this product, okay. So, and then this is happening also, this 9.1% also happening very similar mechanism, but from the other regioisomer. So, this kind of indicates that okay, there is involvement of this 1,4 biradical. Now, the question comes, now as you can see, very important question as you have asked, that head to head or head to tail. So, what is happening here, because if you have a carbonyl group one side in this and then you have a CH2 on the other side. So, here also you have a R group one side and then nothing on the other side, or you can have a substitution. So, there could be a head to head or head to tail product formation, how that is getting controlled. So, the question comes, there is one important thing is steric and the electronic factor. So, we are going to explain them, and then there is also how to understand why we are going to get to head or head to tail. So, what is the easy way to explain the product selectivity. Again, you can have a two different scenario, as I mentioned, that you can have a olefin with a electron donating group or olefin with a electron withdrawing group. So, now the question comes, we are showing here, if you have a if you have a scenario here, electron donating groups, then you form this head to tail 65%, that means this is the major product, and if you have electron withdrawing group, then the head to head is the major product. Now, why that is happening? So, let us try to understand the difference here, because we know that in the carbonyl cases, once you have this N to pi star transition, you know that this is going to form this species, and you can also try to think about. So, now you can think about them also, you can draw them like these also. So, now if you look into it, as I told you before, that once it is forming O dot, that is where you can see is a delta positive, and then if it is a delta positive, this will be delta negative, then there is a delta positive and there will be delta negative. There is electron formation happening. If this is the scenario, then you can think about that if this is my delta positive, this is a delta negative, say, then you can have a olefin, suppose you have a olefin with the electron donating group like here in case of oxygen. So, if you just think about oxygen, then this is giving electron density. So, that means here you will see a delta minus and here you will see delta plus, correct. So, now if you try to recombine them, this side is going to add up here and this side is going to add up in this place. So, that means the oxygen part will be here. So, this will be going to head to tail. And very similar thing, if you have an electron withdrawing group here, if you have electron withdrawing group, if you know that if you have a cyano or any other group that can pull electron density, this will be delta plus, this will be delta minus. So, now it can this side is going to add here and the head is going to add here. So, that is going to be head to head addition. So, that can give to this product. Again you can see some example here where the diastrophysial selectivity is happening, because you can see in this example here you can see you are getting to the so this product and this product, and you can see that, you can clearly see in this reaction the diastrophyselectivity is getting maintained. Then there is another example here, if you have isopropyl group and a methyl group, then the reaction try to take place with this double bond in such a way to avoid the strain with the isopropyl group. So, it try to avoid the, so if you have isopropyl group in this position, then this could have a more interaction with the acetate compared to the methyl group. We have learned about the enone alkene cycloaddition. So, now we are going to move to another important reaction is the dipymethane rearrangement. Okay. So, what is a dipymethane rearrangement? A dipymethane rearrangement is a very important rearrangement reaction. Here what is going to see, it is actually going to if you have a it's going to rearrange the non-conjugated non-conjugated olefin containing 2 pi systems. So, if you have you can have a scenario here, you have a 2 pi system which are non-conjugated, and then by a saturated carbon, it has to isolated by a saturated carbon, and then it is, or it could be a in or aryl substitution. So, now what is going to happen, it can able to do some sort of rearrangement to form very important compounds, like starting from 1,4-diene you can end up making vinyl cyclopropane, or starting from allyl benzene it can end up making a phenyl cyclopropane. Okay. So, it was originally discovered when I think it can also say this reaction as a Zimmermann rearrangement, because the Zimmermann group in 1967 they observed from this important reaction from berylline in place of HNO and acetone, it can convert to semi-bulbilene. So, that is a very important transformation happening, and you can see this reaction used in acetone in place of the UV light, this conversion happen. And so this is the initial discovery about the dipymethane rearrangement. Now, we are trying to understand the the mechanism of this reaction, conversion of this the berylline to the this particular compound. So, how this reaction is happening? You have to understand there is an important thing in this reaction, that this rearrangement actually happen exclusively from the excited states, and then it can go via the singlet or triplet excited states depending if you are using sensitizers. If you are using sensitizer, it is going from this excited states triplet, and if you are not using the sensitizer, it is mostly happening from the excited state singlet. So, what is happening? I think this reaction also depend on the substrate. So, for some particular class of substrates, this reaction happening from the excited state triplet as well. So, here you can see first the acetone which is actually acting as a sensitizer. Acetone can actually go to the excited state triplet. It can transfer the energy to the starting material to convert the starting material to the excited triplet to form this biradical. From the biradical you can see here, it can now able to form this sort of a biradical after cleavage here. So, it can move this way and form this biradical. Now, there is a conformational change happen, you can able to draw that, and now if you think about so this is literally going to form a radical here in the next stage, which there is a radical recombination, because it is going to form a double bond and a radical that can recombine to form this product. So, important thing to remember that you need to use acetone for this reaction. If you do not use acetone, it is not going to form this product, it is going to form something else. Now, we are trying to understand the mechanism of this reaction. First thing is, once you under the UV light, it is going to the excited singlet state. As I mentioned, if the reaction is happening from the excited singlet, then we generally try to write the mechanism in a Juiter ionic form, that you can think about this double bond as a plus minus, and now you can try to push the arrow here, like, and then form a anion here which can combine with this cation to form this corresponding vinyl cyclopropane. Okay. Now if you have the other scenario, it can go from singlet to the triplet state to the intersystem crossing, formation of this 1,4 biradical, and then once you have this 1,4 diradical, it can now have allow this cyclopropane ring opening, because it is going to form the more stable tertiary radical, and after that there is a radical recombination can happen to form this product. So let's try to see a scenario here in this particular compound. So there is a different product forms if you done in the presence or absence of the photosensitizer. So in the presence of the sensitizer, it is forming only what is happening. If you see here, in place of sensitizer, there is a isomerization happening. This olefin which was cis initially become trans here. But if you are in absence of the sensitizer, what is happening is a dipyrmethane rearrangement happening, and you can observe here. So there is a 1,2 shift happening. So you can see there is a 1,2 shift happening from this group to here and this pi bond. So there is a formation of a cyclopropane here, okay, and this group is shifting here. So there is a 1,2 shift happening, and this is happening effectively in the from the single state. And now again in case of the triplet state, what is happening in the triplet state, there is a formation of that. If you have a olefin, that can also excited from the pi to pi star, that can also form this diradical species, which can now able to, so there is a bond rotation going to happen, which can isomerize the olefin. There is another important example here in this particular compound. You can see first formation of this the biradical from this. If you pass the UV light from there, what is going to happen? It can, so there is a hydrogen here. It can go for a 1,3 hydrogen shift to form this 1,3 biradical intermediate. From there it can combine and form a cyclopropane, as I mentioned at the beginning. That it's not always going to form this 1,4 diradical. It can also form a 1,3 diradical. Here there is a so now if you have instead of this hydrogen, if you remove the hydrogen and put 2 phenyl group here, what is going to happen? Now first thing is going to happen, formation of this 2 radical. Now there is no hydrogen for the abstraction. So what is going to happen? This is a stable benzylic radical. It is going to add to the aromatic ring, and now after that what is going to happen? You can see here this radical can also add here. So there is 2 different scenarios. This can add here to generate this radical. Okay, because I think one of the important thing is this is a more stable radical, so this is less reactive. This is another reactive. The homobenzylic radical is going to add here to the aromatic ring. It is a more reactive one, going to generate this radical species here. The next thing what is going to happen, now this is going to try to get aromaticity, and once it will try to get aromaticity, it is going to generate a more stable this diphenyl radical, and from there it can have a radical recombination very similar to the previous step. You can able to end up getting to this product. Okay. Then there is a oxide dipyrmethane rearrangement. If you have carbonyl and if you have a double bond here, then there will be a n pi star transition. Then this radical can able to add here to form this radical species. Now it can open the corresponding. You can see here it can open the corresponding cyclopropane and generate a radical, which can again recombine to form this species. If you have a in these cases also the very similar thing happen. First this n pi star transition happen, then you can see formation of this cyclopropane, formation of this diradical species 1,4 diradical, and here what is happening, you can see there is again very similar thing. This is going to get clipped, because I think the formation of this carbonyl compound is very important, is going back to the carbonyl compound. It's a more stable product. So that's why this cyclopropane going to cleave, form this carbonyl, form this radical here, which is going to be, I think you can see here formation of this carbonyl, and then then you end up making this radical, and then also you end up making this radical here, which is also your 2 methyl group which is stabilizing it. Then finally the radical recombination going to get to this product. And if you have a scenario, in one case you have a dimethyl, you have a diphenyl here, what is going to happen? First thing, under the UV light, it can form this cyclopropane, and there is a formation of this the 1,4 diradical species. But now the depending on the stability, you can see this is a more stable one compared to this one. So what is going to happen? Because this is a more stable, that is going to remain So that is not going to be more reactive. So the one which is less stable here, that is going to open up the cyclopropane ring here to form this radical. At the end, these two radical going to go for recombination to form this product. But the other way it's not happening, as I mentioned, because of the stability of the radical. So I think what is happened in this part. I have talked about the photochemical 2+ cycloaddition. I talk about the enone and alkene cycloaddition. At the beginning I talk about the Paterno-Bucci reaction, the Aja-Paterno-Bucci reaction. At the end I talk about the the dipymethane rearrangement. And actually there are important reference book. You should definitely get to these books of the Nicolas Turo. It's a very good book for the photochemical reaction. And then there are some other references. And again thank you so much for coming to the class. I'm going to see you guys in the next class.